Welcome back to the Deep Dive. I am your host, and today we actually have a bit of a mission. We are going to try to fix a traumatic memory that I think a lot of us share.
That sounds a little ominous. Which memory are we talking about exactly?
You know the one. You're motivated, right?
Yeah.
You decide you want to learn something incredibly complex. Maybe it's general relativity, maybe it's machine learning, or
Mhm.
in our case today, quantum computing.
Oh, I see where this is going.
Yeah. So you go to the bookstore or you go online and you buy the big introduction to whatever book. You sit down, you read the preface, and you feel great. You read chapter 1, which is usually just history, and you feel really smart. And then you turn the page to chapter 2.
And you just hit the wall. Hard.
It is not even a wall, it's a cliff. Suddenly, the English language has just left the building entirely, and you're staring at this dense block of Greek letters, weird brackets, equations that look like, I don't know, alien hieroglyphics.
Yeah.
And you just close the book, you put it on the shelf, and you literally never touch it again.
Yeah, it's the classic chapter 2 death spiral. We see it all the time in academia.
The death spiral.
Yeah.
That is exactly it.
It's the ultimate barrier to entry for almost all modern physics. It is where the pop science ends and the actual real work begins. And usually the author of the book, just kind of abandons you there.
Exactly. And today, we are going to completely dismantle that barrier. We're diving into a source that specifically targets that exact moment of panic for you, the listener. The book is titled Essentials for Deeper Understanding of Quantum Computing. It was published in 2025 by Ryo Maezono. And honestly, this might be the most empathetic textbook I've ever read in my life.
It really is incredible. Maezono captures that learner's frustration so perfectly. He actually asks, right at the beginning, he says, are all introductory books on quantum computers this rigid and excessively difficult?
Which is just so validating.
Right. He's validating the struggle before he even attempts to teach a single concept.
And that is our goal today. We are just going to sit here and talk about what is a qubit in that vague, hand-wavy pop science way. We're not going to talk about Schrodinger's cat being dead and alive and just leave it at that. We are going to walk across the bridge that Maezono built.
We're going to actually look at the math, the linear algebra, the calculus, the notation.
But we are going to do it in plain English.
Right. We're going to look at the actual tools you need to understand how the machine works, not just what it does. Because once you strip away all those scary symbols, the logic underneath is, well, it's actually quite beautiful.
It really is. So let's start with the overall philosophy here. Maezono categorizes learners into two distinct groups. He calls them Type A and Type B. And when I read this, I felt completely seen. I felt like he had been watching me struggle in the university library for years.
It's a really great distinction to make early on. So Type A learners are your classic formalists. These are the people who are already entirely comfortable with the rigorous, traditional style of science.
The math majors.
Exactly. They love the axiomatic approach. You give them a solid definition, then you give them a theorem, then a proof. They do not need a backstory. They just want the rules so they can immediately start calculating.
Yeah, these are the people who sat in the front row of my calculus class and just nodded along while I was basically hyperventilating in the back.
Yeah.
They see a formula and they just accept it. They're like, okay, that's the rule. Let's go.
Right. But then you have Type B. And Maezono says Type B learners often come from fields like information science or engineering or even the humanities. And a crucial point he makes is that they are not less capable.
Right. They just learn differently.
Exactly. They need the narrative. They need to know why we are doing this in the first place. They need the story of the actual discovery before they can bring themselves to care about the equation.
See, I am a Type B learner to my core. If you just show me a bare formula on a chalkboard, my eyes just glaze over instantly. But if you tell me, hey, this formula was invented because some guy in the 1800s was trying to figure out how heat moves through a solid metal bar, and he realized the existing math was completely broken, suddenly, I'm fully invested. I need the stakes, you know?
And that right there is exactly the gap that Maezono identifies in modern education. He argues that most physics textbooks are written by Type A people, specifically for Type A people. They just assume you don't need the story. And he uses this absolutely brilliant analogy of freeze-drying food to describe how these standard textbooks are written.
Oh, man, I loved this part. It made so much sense to me. Breaking it down for us.
So think about the actual process of scientific discovery. When a physicist is in the lab or at the chalkboard figuring something out, say, Schrodinger developing his wave equation back in the day, it is incredibly messy. It's chaotic. There's a lot of intuition. There's guessing. There's hand-waving. There is massive frustration.
Lots of crumpled up paper.
Tons of it. It's a very wet, organic process full of life and confusion. But when they finally figure it out and write it down for a textbook or a journal paper, they strip all of that away.
They completely clean up the crime scene. They hide all the mistakes.
They really do. They organize it into this perfect, pristine, logical chain. Definitions, proofs, results. And Maezono calls this freeze drying. It's a high...
That is such a vivid image. It totally explains why I always felt like I was gnawing on a block of granite in my college physics classes. So the water, in this analogy, is the intuition.
Yes. The water is the historical context, the messy why, the physical, real-world picture. Maezono is saying his book, and by extension, what we are trying to do in this deep dive is the water. We are going to rehydrate these concepts so they are actually edible for you.
And he actually starts the book with some incredibly practical advice on how to physically read a difficult scientific text. He talks about skimming. Now, usually, teachers tell you skimming is terrible. They say you have to read every single word.
Right, but Maezono has a great quote. Skimming is not laziness. Most of us feel this intense guilt if we don't read every single word in perfect order. But he says that for complex physics, linear reading is an absolute trap, because if you get stuck on line 3, you will never even see line 4, even if line 4 contained the exact explanation that would have helped you understand line 3.
He uses this great analogy of cutting through thick cardboard.
Yes, if you take a sharp box cutter and you try to slice all the way through a really thick piece of cardboard in one single heavy stroke, what usually happens?
You slip, you ruin the table, you hurt yourself, or the blade just gets stuck. It takes way too much force.
Exactly. You encounter too much friction and resistance. The better, safer way is to make a very shallow groove first. You just trace the line, you get the general shape, that is the skim. You learn the new vocabulary, you look at the structure of the chapter, you read the main headers. You absolutely do not worry about the gritty details yet. Then you go back for a second pass and you cut a little deeper. Then a third pass.
So for chapter 1 of any quantum book, you just get the lay of the land. Don't stop to verify every single complex equation. Just see where the road is generally going.
Exactly. Build that groove. But, and here is a massive curveball he throws. When he gets to the actual math in chapter 2, he gives the exact opposite advice. He says, close the laptop, put away the PDF slides, go get a physical pen.
He is aggressively anti-PowerPoint for teaching math, isn't he?
Yeah.
He practically bans it.
He really is, and for very good reason. He talks at length about the cognitive connection of handwriting. You fundamentally cannot learn the language of physics just by staring at a screen. It is quite literally a language with its own unique syntax and its own grammar.
It's sort of like trying to learn to write Chinese characters by just passively looking at them on a flashcard. You might eventually recognize them, but you can't actually reproduce them yourself.
Precisely. You have to physically write out the Greek letter psi. You have to write the integral symbol. You have to write all the little subscripts and indices. Maezono says that until your hand can naturally form the symbols comfortably, your brain simply cannot process the logic that they represent. You end up spending way too much of your brain's CPU power just decoding the weird font.
That is a really distinct takeaway for you right off the bat. If you are trying to learn this stuff and you're just casually reading on your tablet on the couch, you are doing it wrong.
Yeah.
You need a physical notebook. You need to scratch the math out yourself.
It forces you to slow down, and that is entirely the point. It forces you to process every single symbol sequentially. It forces you to own the language.
Okay, so we have our underlying philosophy established. We are type B learners. We are rehydrating these freeze-dried facts, and we have our pens ready. Let's get into the actual meat of the content. Our next section asks the really big question. What actually is quantum computing?
And right here, Maezono makes a critical distinction that often gets completely glossed over. Usually, when you hear the phrase quantum computing in the mainstream news, they're talking about one very specific type. They're talking about gate-based quantum computing.
That's one that's supposed to eventually crack all our bank passwords and ruin modern cryptography, right?
Essentially, yes. That is the long-term dream or the nightmare, depending on who you happen to ask.
Yeah.
The fundamental working unit in that system is the qubit.
And this is where we usually get the extremely tired explanation of, oh, it's a 0 and a 1 at the exact same time, which, honestly, I always find super annoying. It feels like a massive cop-out.
Because it is a bit of a cop-out. I mean, it's technically true, but it's not actually helpful for understanding anything. Maezono pushes us to what he calls the standard granularity. He wants us to actually look at the mathematical representation. A qubit isn't just a magical coin flipping in the air. It's a specific state described by two numbers. Let's just call them coefficients C0 and C1.
Okay, so C0 is the amount of zeroness and C1 is the amount of oneness.
Roughly speaking, yes. But here is the major kicker. These aren't regular numbers like 0.5 or 0.3. They are complex numbers.
Complex numbers, so they have a real part and an imaginary part. They involve the square root of -1.
Correct. And because they're complex numbers, they possess two specific properties: amplitude, which is how big they are, and phase, which is what angle they are pointing at. And this naturally brings us to a very famous visualization tool in physics, the Bloch sphere.
I have actually seen this diagram before. It basically looks like a wireframe globe with an arrow sticking right out from the center to the edge.
That is the absolute best way to think about it. Imagine a standard desk globe. The North Pole represents the state 0. The South Pole represents the state 1. Now, in a traditional classical computer, your bit can only be exactly at the North Pole or exactly at the South Pole. You have to pick a side. It is strictly binary.
But a quantum computer.
A quantum computer allows that central arrow, that state vector, to point literally anywhere on the surface of the globe. It can point to the equator, it can point to Australia, it can point to the middle of the Atlantic Ocean.
So that arrow represents the superposition. If it is pointing right at the equator, it is exactly halfway between 0 and 1.
Exactly. And gate-based computing is entirely about moving that arrow around the globe. When physicists say we apply a quantum gate, what we really mean mathematically is we are taking that vector and rotating it. We are taking an arrow pointing at Africa and precisely rotating it so it points at South America.
Okay, but how does that actually solve a complex problem? How does spinning an arrow around an imaginary globe crack a password?
Interference, that is the magic word here. Because these coefficients are complex numbers with a phase, they act exactly like physical waves. You know how waves work in water or sound? If a peak meets a trough, what happens?
They cancel out. Destructive interference. It's exactly like how noise-canceling headphones work. The outside airplane noise is a wave, the headphone plays the exact opposite wave, and boom, silence.
Perfect example. And if a peak meets another peak, they stack and get bigger. Constructive interference. The ultimate goal of any gate-based quantum algorithm is to script a very careful choreography of these waves. You want to mathematically rotate and combine all the qubits in such a way that the wrong answers destructively interfere. They literally cancel themselves out to 0, and the correct answer constructively interferes and gets massively amplified so that when you look at it, it's the only answer left.
That is a genuinely beautiful way to put it. You are choreographing the math so that the error kills itself.
Yes. It is not just the computer trying every single password simultaneously. It's the computer making the wrong passwords mathematically vanish. But, and this is where Maezono shifts gears, his book actually has an entirely different destination in mind. While he does explain gate-based computing clearly, his heart is really with the second major type of quantum computing: quantum annealing.
Now, this is the one I know significantly less about. I feel like it gets way less press coverage. How is it fundamentally different?
Gate-based is like a general-purpose tool. Think of it as a Swiss Army knife. Theoretically, it can compute anything at all if you have enough stable qubits. Quantum annealing is entirely different. It is a massive sledgehammer specifically designed for one single thing: optimization.
Optimization. So basically finding the absolute best solution among billions and billions of possible options.
Right. Think of the classic traveling salesman problem, or figuring out how a complex protein folds, or optimizing a global delivery network for FedEx. These are problems where you have a vast landscape of possibilities, and you want to find the single absolute best one. Maezono uses a really great visual analogy here. Imagine a 2D grid.
Okay, I am picturing a simple black and white checkerboard.
Imagine you desperately want to find the most efficient path for an object moving across that board. You can mathematically map that specific problem to what physicists call a spin glass model. Basically, you turn your logistical problem into a fundamental physics problem. You set it up so you can say, the best solution to my FedEx route corresponds exactly to the lowest physical energy state of this quantum system.
So we aren't actually calculating the answer in the traditional step-by-step sense. We are building a physical model where the answer is just the natural resting place of the system. We basically let nature do the heavy lifting for us.
Precisely. We are tricking nature into solving the math problem for us. But there is a major catch. Imagine that energy landscape we just built. It is not a nice, smooth bowl where a marble just easily rolls to the very bottom. It is an incredibly rugged mountain range. There are deep valleys and high peaks everywhere. The absolute best solution is the deepest valley of all, what we call the global minimum.
But there are lots of other little valleys scattered around.
Well, also-
Local minima.
Yes. And in classical computing, or even with classical optimization algorithms, if you are mathematically walking down the hill looking for the bottom, you might just stumble into a small dip. You look around and every single direction you step is up, so your classical algorithm thinks, well, I guess I'm at the bottom. But you aren't. You are just stuck in a pothole halfway up the side of the mountain.
And you don't have enough energy to climb back out of the pothole to go check if there's a deeper valley over the next ridge. You're just trapped there forever.
Exactly. You are permanently stuck in a suboptimal solution. And this is exactly where quantum annealing completely changes the game. It introduces a vital concept called the transverse field, usually denoted in the math by a capital T.
The source material calls this the secret sauce. I really love that term.
It absolutely is the secret sauce. Imagine that instead of just walking around the landscape blindly, you have a giant dial in front of you that controls an earthquake. A massive, reality-shaking earthquake.
Okay, I definitely like where this is going. We're going fully seismic.
When you start the quantum annealing process, you turn that transverse field dial all the way up to maximum. You shake the entire energetic landscape violently. In quantum terms, this physically puts the entire system into a massive, all-encompassing superposition. It is essentially exploring every single valley at the exact same time. The system isn't in one distinct place. It is a probability cloud covering the entire mountain range simultaneously.
So it literally can't get stuck in a pothole because it is bouncing everywhere all at once. It has way too much energy to ever get trapped.
Right. And then, and this is the crucial part, very, very slowly, you start to turn the dial down. You smoothly reduce the transverse field. This is the actual annealing part of quantum annealing. As the shaking slowly stops, the system naturally wants to settle down. And because of the bizarre laws of quantum mechanics, specifically a phenomenon called quantum tunneling, if you do this process slowly enough, the system will naturally drift, tunnel through the mountains, and settle perfectly into the absolute deepest valley.
The global minimum.
The global minimum. Think of it like vigorously shaking a freshly opened box of cereal to get the heavy toy to settle at the very bottom. The shaking energy allows everything to slide around and find the optimal, most compact packing state. If you just drop the toy in, it would probably get stuck on top of the flakes. But if you shake it, it naturally finds the absolute bottom.
That is surprisingly intuitive. I can visualize that perfectly. The transverse field is quite literally just the intensity of the shake.
It is. But, and here comes the cold water for the Type B learner. Maezono points out that while students absolutely love this visual concept, they routinely fail to ever really understand it deeply because they inevitably get stuck on the underlying math required to formally describe it.
We are right back to the Chapter 2 cliff. The earthquake analogy sounds super cool, but actually writing out the rigorous equation for the quantum earthquake is incredibly hard.
We are indeed back at the cliff. To really, truly understand how that transverse field operates mathematically, you absolutely need some specific mathematical tools. And Maezono identifies two major villains that routinely kill a student's motivation right out of the gate.
Let's name them and shame them for our listeners.
Villain number one is linearization, and villain number two is index handling.
Okay, let's take them one by one. Let's start with linearization. This usually brings up a very specific term, the Taylor expansion. I actually vividly remember memorizing this exact formula back in high school calculus. F of x equals, well, something, a bunch of derivatives. I completely memorized it, but I never once understood what it was actually for. It just felt like tedious, busy work.
That is the Taiki teaching style rearing its head again. Here's the formula, shut up and memorize it. Maezono wants us to see linearization not as a formula, but as a deep philosophy. Linearization is fundamentally the art of aggressive simplification. It is the core belief that simple is always better than perfect.
Explain that to me. How on earth is simple better than perfect in physics? I always thought physics was entirely about being exact and precise down to the decimal.
It is, but exactness is incredibly expensive computationally. Imagine a curve. Any kind of curve. Let's say a wild roller coaster track. It twists, it turns, it goes way up and way down. It is mathematically a very complicated shape. Describing that whole track accurately requires a really nasty, complex function. But what if you just zoom in on it?
Zoom in on a piece of the track.
Zooming way, way in until you are looking at just 1 tiny inch of the steel track. What does that 1 inch look like to you?
Oh, it looks totally straight. I mean, Even a massive loop-de-loop looks flat if you only look at a single millimeter of it.
Exactly. If you zoom in close enough, absolutely everything in the universe is a straight line. That concept is the beating heart of the Taylor expansion. The very first term of the Taylor series is basically just the math saying, hey, let's just pretend this crazy curve is actually a straight line right at this specific point.
So we are essentially trading a very difficult, accurate curve for a very easy, slightly inaccurate straight line.
Yes, because a line is incredibly easy to calculate. Linear equations are the easiest things in math. But naturally, as you physically move away from that one specific point you zoomed in on, the straight line and the actual curvy roller coaster track start to separate from each other. The approximation starts to get worse and worse.
So we definitely need some kind of correction factor.
Right. And that is what the second term in the Taylor expansion does. It adds a bit of curvature. It essentially turns your straight line into a slight parabola. It hugs the real curve just a little bit better. Then the third term adds a little wiggle to it. The fourth term adds another smaller wiggle. A pure mathematician would look at this and say, you strictly need the infinite series of wiggles to be perfectly accurate.
But Maezono was a physicist, not a pure mathematician.
Correct. And physicists famously say life is way too short for infinite series. Maezono heavily emphasizes the concept of truncation. He says, look, if we are only ever looking at a very, very small change in our system, let's call that change delta x, say the change is just 0.01.
Okay, the very small step forward.
What is 0.01 squared?
0.0001.
It's tiny, it barely matters. And what is 0.01 cubed? It's 0.0000001. It is basically zero for all practical intents and purposes. So Maezono says, just violently throw them away, keep the easy straight line, maybe keep the squared term if you're feeling incredibly fancy and need a bit more accuracy, and literally just ignore the rest of infinity.
This is essentially the good enough principle.
It is the absolute foundation of all modern engineering. This is exactly why we can successfully build massive suspension bridges. Engineers do not solve the perfect, infinitely complex equations of the universe. They linearize the system. They basically assume that for very small wind vibrations, the massive steel bridge just acts like a simple linear spring.
Because I guess if the bridge is bending so violently that the squared and cubed terms actually start to matter.
Then the bridge is already catastrophically collapsed, and the math really doesn't matter to anyone anymore.
That is a very fair point. So linearization is purely about zooming in until the world is simple enough to actually solve with the brain power we have. That genuinely makes it feel so much less intimidating. It's not about being mathematically wrong, it's about being practically efficient.
Exactly. And understanding this philosophy leads Maezono to discuss Euler's formula. E to the power of x equals cosine of x plus I times sine of x. This is arguably the most famous, most beautiful formula in all of complex analysis.
It connects exponentials, which I always associate with compound interest and growth, to sines and cosines, which are obviously waves, which always seemed completely weird to me. What does my bank account's compound interest have to do with sound waves?
That is the grand mystery of math. Maezono actually shows the derivation for this in the book, but he openly admits it is what he calls a formal derivation, which is really just a highly polite academic way of saying, we totally cheated to get this.
How so? How do you cheat in math?
Well, if you write out the long Taylor expansion for the exponential e to the x, and then you separately write out the Taylor expansions for cosine x and sine x, and you just blindly plug in the imaginary number 9s into the exponential series, the patterns just miraculously match perfectly. It honestly looks like dark magic. Now, a rigorous mathematician would loudly demand a formal proof about convergence radii to ensure you actually legally allowed to plug imaginary numbers into infinite series like that. They would happily spend 10 dense pages proving you can do it.
But the physicist just steps back and says, look, the puzzle pieces clearly fit together. Let's just go with it.
Exactly. And for the type B learner, Maezono is explicitly saying that is okay. You absolutely do not need to prove the convergence radius to effectively use the tool. Just accept the beauty of the pattern. Accept the fact that exponentials mathematically describe waves. Once you accept that one fact, quantum mechanics becomes so much easier to digest because at its core, quantum mechanics is quite literally just wave mechanics.
That is such a massive relief.
Right.
We essentially have permission from a physicist to skip the rigorous, painful proof. We can just enjoy driving the sports car without needing to know how to perfectly rebuild the transmission from scratch.
Exactly. Just drive the car.
Right, now let's turn and face the second villain. The one that honestly actually scares me a bit, index handling.
Ah, yes. The dreaded subscripts. The little I, J, K, L, M dangling at the bottom of every letter.
This is exactly where I always get hopelessly lost. I
Yeah.
look at a textbook page, and I see an equation with 3 different little microscopic letters at the bottom of every single variable, and my brain just instantly shuts down. Maezono says this specific issue is the #1 reason students drop out of advanced physics courses.
It absolutely is, because students naturally try to visualize the whole massive geometric object in their head, rather than just trusting the individual mathematical components. To fix this, Maezono formally introduces the Einstein summation convention.
Which, I have to say, sounds incredibly fancy and terribly difficult. The Einstein Summation Convention. It sounds like a complex international treaty signed in Geneva in 1945.
It does sound intimidating, but it is actually born entirely from profound laziness. Einstein was writing out these massive, sprawling tensor equations all day long. General relativity obviously has a ton of indices, and he just got completely exhausted from drawing the summation symbol over and over again. You know, that big, jagged Greek letter sigma.
So he just decided to stop writing it.
He literally did. He just made up a new rule for himself. If you ever see an index repeated in a single term of an equation, you just automatically assume you have to sum over it.
Walk me through that. Give me a concrete example.
Okay. Suppose you have 2 simple vectors, vector A and vector B. If I write A subscript I multiplied by B subscript I...
Okay, the I is repeated twice there.
Right. So under his rule, that automatically means A1 times B1 plus A2 times B2 plus A3 times B3. It's just the standard dot product. You just sum them all up. You don't need the big sigma telling you to add them. The visual repetition of the letter I is itself the command to sum them up.
Well, that seems simple enough. It really cleans up the clutter on the page.
It is incredibly clean until you suddenly have multiple different sums happening at once. This is where Maezono strongly warns about the dummy variable trap. That little index I or J or L, it's just a dummy. It has no actual soul. It is purely a temporary counter. Writing AI gives you the exact same final number as writing AKB.
Because once you actually do the addition, the I or the K just totally disappears anyway. It just becomes a single number. It's kind of like a temp worker. They come in, they do the specific counting job, and they leave without a trace.
Exactly. But here is the exact spot where students mess up terribly. Suppose you have 2 separate sums that you want to multiply together. So you have AIB and you want to multiply that whole thing by CD.
Wait, that immediately looks wrong to me.
Because it is fundamentally wrong. You've used the exact same dummy letter I 4 times in one term. The convention completely breaks down. The math now implies you are trying to sum all 4 of those things together simultaneously in some weird 4-dimensional hypercube way. You desperately need to keep your dummies distinct from one another. You should have written AIB multiplied by CJDJ.
Keep your dummies distinct. Honestly, that is just incredibly solid life advice right there.
It really is. Now, moving past the dummy trap, there are 2 highly special symbols Maezono heavily focuses on that essentially unlock all of vector calculus for you. They are the Kronecker delta and Eddington's epsilon.
Again with the names, these genuinely sound like titles of Robert Ludlum spy novels. The Kronecker delta protocol.
They do, but the Kronecker delta, written as a little delta with an I and a J, is going to be your absolute best friend. It acts exactly like a filter, and it has one incredibly simple rule. If the index I and the index J are the exact same number, the value of the symbol is just 1. If they are different numbers, the value is strictly 0.
So delta 1, 1 is 1. Delta 1, 2 is 0. It's just a binary switch.
Right. Now think about what happens when this thing interacts with the sum. If I have a massive sum of items, and I throw in a delta ij as the sum count through j equals 1, 2, 3, and so on, the delta acts as a 0 for absolutely everything, except for the one single moment when the counter j hits the specific value of I.
So it ruthlessly kills every single term in the long list except for 1.
Yes, it pins the floating index, it grabs the exact value you want, and aggressively throws all the rest in the garbage. Maezono actually calls this a pinning operation. It allows you to instantly simplify massive, terrifying equations by just deleting everything that doesn't perfectly match.
That sounds incredibly satisfying to do. You just take your pen and cross out all the non-matching terms. It's like having a bouncer at an exclusive club who only lets one specific person from the line inside.
It is exactly like a bouncer.
Okay, so I definitely like the pinning delta. What about the other one? Eddington's epsilon. The source also calls it the permutation symbol.
This one is the absolute nightmare for beginners. It looks like a little epsilon, but it has 3 distinct indices, I, J, and K.
Why on earth do we need 3 of them?
Because we live in 3 dimensions, and it's built specifically for the cross product. You know the old right-hand rule from high school physics. If you take vector x and cross it with vector y, your thumb points to vector z. But if you reverse it and cross y with x, your thumb points down to negative z.
Yeah, so spatial direction definitely matters. The order matters.
Exactly. The epsilon captures that exact handedness mathematically. Think of it as a strict traffic cop. It looks at the specific numerical order of the indices I, j, and k. If they are in the natural order, like 1, 2, 3, or cycling forward like 2, 3, 1, it gives you a positive 1.
Thumbs up, green light from the cop.
But if they are out of order or anti-cyclic, like 2, 1, 3, the traffic cop gives you a negative 1.
Thumbs down, red light.
And if any single index repeats like you have 1, 1, 2, it instantly gives you a hard 0.
A 0. Why 0?
0. Because you physically cannot take a cross product of a vector with itself. They are parallel, so there is no cross area.
Ah, okay, that makes perfect logical sense.
So this terrifying-looking symbol is literally just a tiny machine that spits out a +1, a -1, or a 0 to strictly dictate the 3D orientation of your vectors. Maezono points out that if you can truly master the bouncer delta and the traffic cop epsilon, you can effortlessly derive almost every single complex identity in vector calculus without ever once needing to draw a 3D picture. You stop trying to do messy geometry in your head, and you just start doing clean algebra on paper.
That really shows the sheer power of the tool. It entirely separates the raw calculation from the painful spatial visualization, so your brain doesn't just overheat and shut down. You just trust the traffic cop and the bouncer to handle all the messy details for you.
Exactly. You absolutely don't need to try and visualize 3-dimensional vectors wildly spinning around in your head. You just follow the simple rules of the indices.
Okay, so let's move on to section 5 of our deep dive, matrices. Now, we normally think of a matrix as just a boring spreadsheet of numbers, just a rigid grid. But Maezono uses a phrase to describe them that I found really unexpectedly poetic. He talks about remaining in the same village.
It is a very poetic way to phrase it. He's talking about the concept of linear operator.
Let's unpack that imagery. The village.
So imagine we have a vector, just an arrow in space. We mathematically apply a matrix to it. The vector gets stretched out, it gets rotated, it fundamentally changes. But, and here's the key, remaining the same village means we are still capable of describing that brand new, stretched out vector using the exact same underlying coordinate system we started with.
So we haven't been forcefully kicked out into some bizarre, twisted dimension where our standard rulers suddenly don't work anymore. We're still living in the same mathematical space.
Right. The matrix is essentially just a local dictionary. It precisely translates the old vector into the new vector, but it keeps everything entirely within the same known language. And understanding this spatial concept leads us directly to the true physical meaning of the determinant.
Oh man, the determinant. I vividly remember calculating determinants by hand. You multiply the main diagonals, then you subtract the opposite diagonals. It was incredibly tedious. And the worst part was I never once knew what the final number actually meant. It was just a pointless mathematical hurdle I had to jump over to pass the test.
And this right here is probably the biggest tragedy of standard math education, because the determinant has a beautiful physical meaning. It is quite literally the volume scaling factor of the matrix.
Like actual physical space.
Yes. Imagine you have a tiny little perfectly square box, a unit cube defined by your basic coordinate vectors. It has a length of 1, a width of 1, a height of 1. So its volume is exactly 1. Now, apply your transformation matrix to that space. That perfect little cube gets violently stretched and skewed into a slanted, leaning box. A parallel pipette, technically.
A squashed, slanted box. Got it.
The precise volume of that newly created slanted box is the determinant of the matrix.
So if I calculate a determinant and the answer is 2, that physically means my little box just perfectly doubled in overall volume.
Yes, exactly. If the determinant is 0.5, your box shrank by half. And here is the massive aha moment that ties it all together. What if you calculate it and the determinant is exactly 0?
Well, the volume of the box is 0.
Right. And what does a 3D box with 0 volume actually look like?
It's completely flat. It's just a pancake or a piece of paper.
It is totally collapsed on itself. It has been crushed from a 3D volume down into a 2D sheet, or maybe even a 1D line or a single dot. This is the exact reason why your math teacher always told you that you cannot invert a matrix that has a 0 determinant. You literally cannot unflatten a crushed pancake back into a perfect 3D cube. You have violently lost the physical information about how tall that box used to be.
That is just brilliant. So when you get a rank deficiency error in a computer program, it isn't just some abstract, annoying coding error. It physically means you have crushed your data's dimensions.
Yeah.
You basically stepped on the box.
You irrevocably destroyed the information. Maezono really hammers this specific geometric intuition home because in quantum computing, perfectly preserving information, which is called a unitary transformation, is the entire name of the game. You absolutely cannot have zero determinants in your quantum gates. You cannot lose the data. The overall probability of the quantum state must always be perfectly preserved.
This leads us perfectly into section 6. If matrices can be this messy and they can skew and twist things all over the place, how do we ever force them to behave? Maezono talks about eigenvalues as the ultimate quest for simplicity.
Yes. The quest to find the one perfect perspective.
What exactly do you mean by perspective here?
Well, imagine a matrix that is just mathematically horrendous. It takes a simple vector pointing straight down the x-axis and violently turns it into a messy mixture of x, y, and z. Everything is deeply coupled together. Every single dimension affects every other dimension. It's like pulling a tangled ball of headphone wires out of your pocket. You pull on one single wire, and the entire knotted mess moves together.
A complete mess, impossible to solve cleanly.
But we have to ask a philosophical question. Is the mess actually inherent to the physical system itself, or does it just look messy because we are stubbornly looking at it from a really bad angle?
So we basically just want to tilt our head to see it better.
Mathematically, we want to rotate our entire basis. We want to find a brand new set of coordinate axes where the matrix suddenly stops mixing everything together. We are actively hunting for what we call eigenvectors.
These are the magic vectors.
They are the specific magic vectors that, when the messy matrix hits them, they fundamentally refuse to rotate. They stubbornly refuse to change their direction or mix with the other axes. They just sit there on their tracks and either get uniformly longer or shorter.
And the specific amount that they stretch or shrink that number is the eigenvalue.
Correct. And here is the absolute magic of it. If you completely rebuild your coordinate system out of nothing but these stubborn eigenvectors, your incredibly nasty, tangled matrix suddenly and miraculously becomes a perfect diagonal matrix.
Which means it has numbers down the main diagonal and just pure zeros everywhere else.
Exactly. Zero mixing. Zero tangles. You have effectively turned one incredibly difficult coupled 3D problem into three incredibly simple, entirely independent 1D problems. This process is called diagonalization. Maezono actually links this directly to the deep principles of group theory. It's all about methodically hunting for the hidden symmetry that simplifies the universe.
So bringing this back to physics, when we talk about the specific energy levels of an electron inside an atom, those distinct levels are just eigenvalues.
They absolutely are. The famous Schrödinger equation is, at its core, just a complex matrix operator. The physical states of the atom are the eigenvectors, and the actual measurable energy is the eigenvalue. The atom naturally wants to settle into these specific diagonal states because they are perfectly stable. They are the fully untangled states of nature.
It is genuinely amazing how these dry, abstract math terms that we hated in school turn out to be the literal fundamental architectural blueprints of reality.
That is exactly what Maezono is trying so hard to show the Type B learner. The math isn't just an arbitrary hurdle placed there by an angry professor. It is the actual physical skeleton of the universe.
Which brings us beautifully to the final major tool in our quantum toolkit today. Section 7, differential equations. The language of describing how things fundamentally change.
Maezono uses another really great simple physical analogy here about throwing a ball through the air.
I really like this one. Two young students are outside. They both throw a baseball. One throws it really high up in a big arc, and the other throws it on a low, flat trajectory.
Right. Now, to a totally primitive observer, someone who doesn't know anything about physics or math, those are two completely distinct, unrelated phenomena. They see a high throw and a low throw. They look totally different, so they must be fundamentally different things.
But the trained physicist looks at them and sees them as the exact same phenomenon.
Because they are both strictly governed by the exact same universal law, Newton's laws of motion. The equation F equals ma is completely identical for both baseballs, regardless of the arc. The underlying differential equation is exactly the same.
So then why do they look so different to our eyes?
Because of exactly how they started their journey, the integration constants.
Ah, the initial conditions.
Precisely. When you actually solve the differential equation, when you perform the integration, the math naturally spits out these blank, unfilled spaces for the initial conditions. Where exactly was the student standing? What specific angle did they throw it at? How hard did they push it? The differential equation represents the pure universal rule. The integration constants represent the specific, messy story of that one single throw.
I really love that concept. The complex math aggressively washes away all the messy details to expose the pure universal rule, and then the integration process carefully puts the human story back into it so we can see what actually happened.
And in the realm of quantum mechanics, we are primarily dealing with wave equations. And this brings us right to the doorstep of the Fourier series.
The concept of stacking waves.
Yes. The profound realization that literally any wave, no matter how weird or jagged it looks, a sharp square wave, a single isolated pulse, just pure jagged static noise can be perfectly mathematically constructed just by meticulously stacking up simple, smooth sine and cosine waves.
It's exactly like digital Lego bricks. You can theoretically build a perfect complex model of the Death Star out of just basic, simple, rectangular bricks if you have enough of them.
A perfect analogy, yes. And recall our good friend from 10 minutes ago, the eigenvalue. Why do we always use sines and cosines to build these things? Or the exponential e to the ekx? Why do we specifically choose those smooth shapes as our Lego bricks?
Why do we?
Because they are the ultimate eigenfunctions of the derivative itself. If you take the derivative of the function e to the power of x, what exactly do you get?
You just get a multiplied by e to the x.
Exactly. It is the exact same function you started with. It just scaled up by a factor of x. It absolutely refused to change its fundamental shape. That is precisely why they are the universal building blocks. They are basically the eigenvectors of calculus. They are the natural native language of change.
Okay, that click just visibly happened for me. We use them simply because they play nice with the machinery of calculus. They are the specific shapes that actually survive the violent mathematical operation of change intact.
They play incredibly nice. And finally, to tie the whole quantum picture together, Maezono talks about boundary conditions. Imagine a physical guitar string.
Okay, I have my finger on a fret and I pluck the string.
Now, the pure wave equation dictates that the string can theoretically vibrate at any possible continuous frequency, but you have physically pinned the string down. You are holding it tightly at the metal bridge and you are holding it down at the nut. The string cannot move at those two specific ends.
Right, so I have severely limited its options. The wave I create fundamentally has to fit perfectly inside the space between those two pins.
Exactly. You physically force the continuous math to suddenly become discrete. You can only produce the fundamental note, the strict octave, the fifth. You mathematically cannot have the messy in-between frequencies because the wave wouldn't fit perfectly between the pins.
And that right there is where the word quantum in quantum mechanics actually comes from.
Exactly. It's not magic pixie dust. It's not science fiction. It is purely a boundary value problem. An electron is essentially just a wave that is physically trapped inside the tiny box of an atom. And because it is trapped by those boundaries, it can only legally possess specific, discrete energy levels. It is physically quantized by its own boundary.
And we've covered so much conceptual ground today. We went from being totally terrified of the Chapter 2 cliff to casually understanding the physical geometry of determinants and the underlying philosophy of Taylor expansions.
We really did. And that is the true beauty of Maezono's book. He isn't trying to magically turn you into a pure mathematician. He is simply trying to give you the necessary Type B narrative so you can actually survive and thrive in a Type A academic environment.
So let's just do a quick recap of the mental toolkit we've built up over the last hour.
All right. We have linearization, which is the vital art of deliberately making complex curves straight so our brains can actually solve them. We have index handling, which is essentially the lazy physicist's brilliant way of doing multidimensional vector algebra without ever having to draw a confusing 3D picture.
We have matrices, which are just local dictionaries for projections inside a village where the determinant immediately tells us if we've accidentally stepped on and flattened our data box.
And we have eigenvalues, which represent the ultimate search for the single perfect perspective where everything naturally unmixes and becomes simple to solve.
And finally, we learned that quantum computing itself, whether we are talking about gate-based wave interference or that truly fascinating quantum annealing earthquake, is completely built on these exact mathematical foundations.
Right. You just cannot deeply understand the annealing process, how that massive system actually physically finds that deep global minimum without first understanding the concept of an energy landscape, which is linearization, and spin states, which are eigenvalues. These equations aren't just arbitrary hurdles to filter out students. They are the actual control dials of the quantum machine.
I honestly feel so much better about the idea of picking that textbook back up off the shelf. Maezono really did build a solid bridge over the cliff.
He absolutely did. And I really want people to remember his final piece of advice on formal derivations. It is completely okay to cheat just a little bit when you are learning. It's okay to just blindly accept Euler's formula just because the pattern is beautiful. Don't let an obsession with mathematical rigor completely kill your natural curiosity.
That is the ultimate Type B superpower. We care infinitely more about the story and the meaning than we do about the rigorous proof.
And the story of quantum mechanics is without a doubt the most fascinating story in science right now.
So here's my final challenge to you, the listener, as we wrap this up. Do exactly what the experts suggested earlier. Go grab a blank piece of paper right now after you turn this off. Just write down Euler's formula, e to the I pi plus 1 equals 0. Write down a simple Kronecker delta subscript ij. Just let yourself physically feel what it's like to write the language of the universe. You might actually be incredibly surprised at how much less terrifying it looks when it's written in your own handwriting.
It really does turn those alien hieroglyphics into your own personal notes. It makes the universe yours.
Thank you so much for diving deep with us today. Hopefully that intimidating Chapter 2 wall looks just a little bit more climbable to you now. We'll see you on the next deep dive.
Keep learning.
Bye for now.